Pleasure to welcome Professor Ravi and Mazumdar. So he was educated at the IIT Bombay, Imperial College London, and he obtained his PhD in control theory under Professor Acquistion and UCLA in 1983. He is currently University Research Chair Professor at the Department of EC at the University of Waterloo at Ontario, Canada, and he has been there since September 2004. Prior to that, he was a professor of ECE at Purdue University. And since 2012, he is a TJ Distinguished Visiting Professor at IIT Bombay, India, and since May 2019, an adjunct professor here at TIFR. He is a fellow of IEEE and Royal Statistical Society. He is a recipient of the Infocom 2006 Best Prior Award, at ITC 2015 Best Prior Award, and the Performance 2015 Best Prior Award, and was runner-up for the Best Prior Award in Infocom 1998. His research interests are in stochastic modeling and analysis applied to complex networks and statistical inference. So without further ado, over to Professor Ravi.
Thank you. First of all, of course, it's a pleasure to be here. It's after, I'm in Bombay after 3 years. I mean, all of us can say that, you know, wherever we go, it's after many years. And so it's, so I was coming to Bombay more on a personal reason. And I sent a message to Salient that I was hoping to pass by just to say hello, and I said we would talk. So what I'm going to talk about is the work of a recently graduated PhD student on really bidding and learning in real-time auctions. And I believe I'm particularly happy about this work because this problem was really posed by a company, a company called Addictive Mobility in Toronto. And they first posed this problem to me about, and it's also with Peter Marbach of University of Toronto. We were at a cocktail reception where the CEO of this company said that, you know, we do ad placement on mobile apps. And we have a very profitable company. In fact, they were ranked as, you know, they have like every country has top 50 under so and so and so on. So one of those companies in Canada is a high ranking thing. He says, you know, we've been running these algorithms, but I'm sure that some math can be put to it. But I have looked everywhere and I find nobody has really worked on these type of problems that we have. And so then we looked at the literature and we found that the literature was really, nobody had formulated the problems that these people wanted. But moreover, all the papers that had been written were just highly stylistic, you know, just learning with some IIT observations and so on and so forth, which really didn't make, it could not help us get anywhere. And you know, you can, in fact, one of the things is that we had a postdoc actually who came from IIT Bombay, and poor guy spent a year with us, and he couldn't make any advances, okay? Because really it is so scant. And we tried many versions of the formulation, and ultimately I think we began to understand the problem. And I think we have a very nice solution to this problem. And so this is what I would like to talk about. Okay, good. So what is the problem basically about? Suppose, so I'll give you the example is when you open up a web page, there are certain positions on a web page where an ad can be placed. And what is the procedure? It's typically the advertisers who wish to place the ads, and the publisher is the person who owns the web page who has that spot on which this ad is being placed. And the way it's going through is there is some transaction at an ad exchange, which I will get into very shortly. And that transaction done at the ad exchange then gives a decision as to whether this advertiser's ad can be placed there. So what is the whole mechanism? You'll see very shortly. And so what I'm going to talk about today is ad auctions, what they are and how they are run. And then I come to the point of what information you need to do a real-time bid. So what I call the information state, and I give us generative model because it is this model that by trying to model and understand it, that we began to get the basic mathematical foundations of this model, of this problem. And then I'll talk about the real life problems of what are called targeting sets and campaigns, and then this the key is this notion of supply curve and problem formulation. And then I talk about certain structural properties associated with this entire set of problems. And what I call the first and second price options, they have a particular nice structural format. And then I will conclude with some of the more recent stuff. So, to recapitulate what thing is, what do we need to know to formulate the problem? What can we say about the market dynamics? How can you formulate the problem that I am going to talk about in both what is called the first and second price auction case, and then talk about these various issues, which are more technical. And the first point, which is what do we need to formulate the problem and the market, actually took us 2 years. Okay? Because they gave us data, the company Addictive Mobility gave us a lot of data. And they said, here's data, and this is what we did, this is what we bid, this is what we won, and so on and so forth. And the question is, not having a model, not having anything, how could you infer what was going on to make the decision? Was the big challenge. And so this is really what. So a company like Additive Mobility is called a DSP, okay, a demand side platform. So what are demand side platforms? They're just aggregators of people who wish to place ads. So for example, you would have Coca-Cola, Honda, they would have various Pepsi, perhaps not Pepsi, but other people who wish to place ads, or maybe a hardware store and so on, which wish to place ads when web pages are opened up based upon the characteristics of what is called the targeting group that they wish to address, which could be age, sex, ethnicity, location, and other preferences, right? So there are a multitude of preferences. And an ad that, say, for example, I always give this example, Honda. Honda in Toronto targets, if you do, on particular apps which are used by South Asians, right? Click info, whatever, things that South Asians would look at, Bollywood songs, movie, Indian grocery stores and so on. Whenever they do a search, these ads come up. And these ads are therefore, they know that the person who's opened the ad is perhaps a South Asian thing. And given that they're in Mississauga, which is a city of 700,000 with a population of about 65% South Asian population. Okay, so they know that you're coming in from Mississauga, so this is perhaps your ethnicity and so on. And so they immediately, when you log on to the web page, so the user logs on to the web page, this information is sent. And there are various people, so a DSP is nothing but an aggregator who actually manages a lot of campaigns. And I'll tell you why it's important. The role of a DSP, not only is so-called the economies of scale, but by running many parallel campaigns, when these spots come up and, there could be this sort of information about this user having certain characteristics. It could be satisfied by a number of ads that could be placed, right? Not just Honda, it could be something else, and so on. So when they try to bid and they try to win, they can also decide to which advertiser they will allocate that ad space to. Okay.
So Salient Info and all these places are registered with this DSP that our advertisement you will manage.
Yes.
That's what it is.
So a very typical contract is signed is, let's say Coke will come to these guys and say, run for 2 weeks an ad in this locality, in this region, targeting this, let's say, age group, and we will pay you, and you must run at least on average 100,000 ads. And usually they have some market data which says that when you run ads, what is the rate at which people click on it or show interest.
So it's not just advertiser like Coke coming in, it's also web pages where we show the ads. So that also is part of the negotiate contract business.
No, the web page, no. The web page will just when you open the web page.
No, but for which web pages does the DSP have?
Yeah, because the moment you open up a web page, a lot of your information gets transmitted to the ad.
To some DSP, right?
Yeah.
Not to one.
No, to all. And many DSPs can bid on it.
Okay.
So it's the ad exchange that gets this information about when you open the web page. The ad exchange says this is a user who has opened the web page in Mississauga, and therefore is this age group and so on.
Any person opening a web page anywhere in the world goes to this ad exchange.
There are 3 or 4 ad exchanges.
3 or 4 ads.
There's one in New York, there's one in Toronto, there's one in San Francisco. Okay. So these are the so this message is sent and the DSPs will pay. And the way what happens is that their bids are then go back to the exchange, and depending on the type of auction that is run, typically they use second price auctions, which is that the highest bidder wins and pays the second highest bid. Okay, but increasingly they also use first price auctions. Google is using first price auctions, where there's a connection between the two, and that's what I'll talk about. And this whole process of showing the particular ad, so whichever DSP wins, the DSP decides, well, I'm going to allocate this because of this particular characteristics to this, and I have to meet this person's requirements of showing 100,000 ads in this 2-week interval. And right now I've shown only 20,000, so maybe I should show this ad to this rather than to some other ad, because they make this decision. And then it's displayed to this thing, and this whole process takes 100 milliseconds.
So DSPs are competing with other DSPs.
Yes, and that's how the bids come about. And this is typically a simple thing. You have an ad exchange, so you have various types of bids that are coming in, and so the first price. So this guy will always win the bid. So this DSP will always win the bid. So if the first price auction, this will be the cost to the DSP. If it's a second price auction, the cost to that DSP will be the second highest. Okay, and that's what they pay.
So this bidding is happening every time there is a request to the web page?
Yes, every time you open a new web page, this is happening. Anybody open the web page, not users, anybody. So on a mobile app, the moment you open up the app, there's a space to put an ad, and then somebody comes.
So you said that the bidding process is a per request auction that happens, and not like you bid and this person wins the bid for this.
No. Every time, that's why it has to be done in 100 milliseconds.
So each DSP is aware of how much bid other DSPs are placing?
Pardon?
So each DSP is aware of how much bid other.
No, that's the point. And there is another very important aspect of this auction. Is the DSP which loses, so like this guy, does not know what was the price paid. So they only can observe the price if they win. Otherwise, they don't observe the price. So this is one of the this is a censored observation case of a problem where you can only observe the price if you win. Otherwise, you get no information. Okay.
Sorry, stupid question. So somewhere in this, there must be an incentive to match the ad placed to the user's profile.
That's exactly what you want to do.
But who has an incentive and why? So
there's a requirement. It's not an incentive, it's a requirement. So Coke will say, that you should target this audience. Honda will say, target these people. In this age group, say, let's say 45 to 60, so if it's selling a Honda Accord, target these people living in Mississauga that are likely to be Indians or Pakistanis. They will buy Hondas and they will buy Honda Accords. That type of stuff, right? No. So they have some historical data, market data.
But if DSP doesn't do well for you, if they don't bid correctly, then you go to some other DSP, right?
Exactly. That's the only thing. So that is the criteria. Okay. If the DSP is, if I give a contract and the DSP is not meeting my contract over time, then I just choose some other DSP. But why is it still preferable than Coca-Cola or Honda doing it by themselves? Is because if they're a single individual, where the strategy will change because they don't have a chance. Every time they have to make a decision, am I going to bid or not? Right? Whereas a DSP doesn't have to worry about this because the DSP says, I'm going to bid in this slot. And depending on who, if I win, I know who I can allocate it to one of these contracts. You see, that's why people go to DSPs. Okay, so first we formulate the source problem with DSP. So the basic approach is obtain what I call impression, which is this idea of showing the right ad, and then allocate to the contract. Or it can do another dual problem of just bidding to satisfy a particular contract. And there are two aspects. This is actually the mathematics shows about it. These are very beautiful things that comes from sort of duality theory. Okay, and that has also very important implications in learning, and I'll tell you at the end. And so we will see how to characterize the bidding prices and the allocations, and then address the problem when the critical information that we need in the first part is unavailable to us. And this problem of sensor observation, and then I'll show the thing. So consider a bidder who bids X for an item that becomes available in an auction. So the first notion we have is the notion of a supply curve. It is just nothing but a distribution function that characterizes the competing bidders by giving the probability of winning an item given that the bidder places X. So it's just a distribution, and I'll call it W, and I will assume for the stock that a density exists, so W prime exists. It's strictly not necessary, but the whole case where a density does not exist, we have done in a paper in Sigmetrics in 2020. You just see it's a very long paper, and I don't think it adds anything. And one of the key things in that paper we didn't realize was the structure that I'm going to expose now. So let's first start with a generative model of bidding, how to think about this problem. So suppose at the time T there are NT bidders, and the bidder behavior is characterized by two things: Bij, which is a bid, and Rij is the probability that a bidder I will bid for an item J. Okay, and the bid placed is Bij, and the entire state of the market, including NT, will be denoted by some capital thing. And since the winner of the auction is the individual submitting the largest bid, Wj will be the maximum of all the bids. And given that it is a second price auction, if I take myself out, it's the maximum of the remaining random variables. And so if I bid X, I'm interested in the probability that that number W is smaller than my X that I bid. Right? And I'm going to pay W. So the win probability, Wx, can be calculated in terms of all these parameters this way. So I'm not going to get into that.
Bidders know the number N. The number
So now just see, we come to it a little bit more. So now we're going to market in equilibrium. So let's assume that the bidders arrive at the Poisson process at rate rho. Then NT, which is the number of bidders at any time, is just an mg infinity process. And if you plug in this mg infinity with the Poisson distribution, you can actually show that Wx is precisely related to the rate of the Poisson process times the bid distribution and the rate distribution. Right? So you can show all of this. But basically what it says is this is the quantity that we need of interest, and it comes naturally from your market model.
Right. For this Wx, you have to assume something about the other bids, right?
Yeah, you just assuming they are independent of you. They're bidding independent of you.
But so there's some distribution for that.
Yeah, we don't know what the distribution is. Right? But right now we'll see. So this is just to show that you can do it in point process and so on. So the average rate is this. Okay, lambda j, which is the average rate at which it arrives, and Wjx is the probability that your bid xt, which you placed, is a probability that the actual price is less than the bid that you win. So that's the probability of winning in some sense. And we call this lambda j Wjx. I've just taken out t for the time being, assuming things are stationary, is the supply curve for problem J. Now, what do I mean by supply curve problem J? So this is actually some data measured on the ad exchange. And you see that these are the impressions, this is the total number of impressions that are available, and these are the bit values. And you see it forms a distribution, which is like a distribution function. It's not a probability distribution function because this is not normalized to 1.
What is the point of this called mean?
So it says if I bid 4 units for this targeting group, I will get 20K ads. Okay? Because remember, when these web pages open at a given instant,
So that is okay, but you wanted some sense of frequency or the probability that if you make value.
yeah. So if you normalize over that, you can convert this into a probability.
So, do we assume that this person whose bid is X is aware of other people's distribution?
No,
At least they're bidding?
that's the key.
Okay, but with,
But I'm just saying that for time being, let us assume we measure it. This is based on past data by which you could measure it.
okay, so if this person who's bidding X is aware of everybody else's distribution, at least they are bidding.
They don't know.
Then shouldn't this be a function of other people's distribution?
But you see, it is assuming that everybody is bidding for a given thing and there's a stationary situation where they are bidding independently on a given item. So there is some distribution from which it's emerging, but they don't know the distribution. But here is a question of this is in taking data from the exchange and going back and estimating this is what the distributions were, probability distributions were. Does that answer your question?
Okay, so this is the data that we would like to fit in some model.
Yes, so this is what we would like to fit in a model, but we don't know the exact.
And in the model, we are assuming that the number of bidders is off and
Yeah, we just assume they arrive randomly
yeah.
and it follows the Poisson process and it satisfies, and therefore in equilibrium will be given that it's 100 milliseconds when this process of bidding takes place. It becomes an MG infinity process with that 100 millisecond holding time.
And how much are they bidding? So each person is bidding.
BIJ independently, they're bidding random amounts. Right?
Is it all identical across
Well,
bidders?
the belief is that all DSPs are bidding similar quantities on the targeting groups that they think. I'll come to that question later on. Okay, I'll come to that structural result later on. But they're bidding a random number, Rij. That's what I call it. See, let's go back. Yeah, RIPI. So these are, you can think of random quantities drawn from that distribution, which the people are bidding. Because okay.
Okay, so we try to assume that there is some sort of distribution from which these people bid.
Yeah, that is, people believe that there's some underlying distribution and they're going to bid on it. But later on, I'll just come to that. Later on, if you just hold, if you get the answer more towards the end of the talk, okay, than the beginning. So let's, for the time being, assuming we have these supply curves. So let's set the problem. Is there what are called M item types, which are the targeting groups. So the M types of targeting group. So targeting group 1 and so on. I'll show you what this is. There are N campaigns or contracts, and without loss of generality, we say a contract I has a duration 0 to Ti, so it's a time deadline by which the contract must be fulfilled. And the set AI, which is a function of this targeting group, says the set of item types that can be allocated towards contract I. So contract I might have many requirements, right? Age, sex, ethnicity, and so on. And so each one of that could be part of the AI, but so what we're saying is that if I do Honda, it might be enough to, certainly it looks at people in the age group, let's say 45 to 60, and it looks at South Asians. So these could be the AIs, okay? And CI is the number of impressions required by the contract at the end of this time Ti. And for simplicity, I'm just going to assume this, but this is not necessary. Okay? And so what happens is these, you could think, are the characteristics of the targeting groups that you have. So they're overlapping because many of them could have similar things. Okay, requirements. So for example, age group 45 to 60 may be true for many of these targeting groups, but these aspects are not present in these other targeting groups. Okay, and the first thing is to know is that such a group can be broken down into the set Bj, where Bj's are now distinct, and in some sense, you see the whole optimization must be done over this space and not this space, because there are many things which are overlapping. So in all previous work on ad auction space, they always consider only one targeting group. And this multiple, actually you need to do this breakdown. So this is what comes when you take practical problems as opposed to writing a theory paper. Okay. So what we'll say is Wjx is, let's call, the supply curve associated with some object in this spaces, in this space of the target group decomposition. Okay, so now what is the first price auction? In a first price auction, on average, we will pay exactly what we bid. Since we bid X times Wx, this is the expected amount you will pay in a first price auction. And in a second price auction, since you're going to pay the second highest price, it is just the integral of this, which is xwx. And so you immediately naturally get the conclusion that in the second price auction, you're always going to be paying much less than if it were run as a first price auction. But there's something very remarkable we found in the theoretical results that we actually got. That if you want to run a first price auction, pretend it's a second price auction. Because your strategy to win, because you have to be the highest bidder to win in both auctions, is very similar to second price auction. Only what will differ is what you pay. Okay. So this is the problem formulation. So remember, these are these, whether it's the first or second price auction, that function, which is, this is what is called the payment. So this is the amount allocated of item J to contract I. So you sum over all contracts and sum over all targeting group types. You've got to meet the capacity constraint, which is the number of options over your period 0 to Ti. And for simplicity, I took all the starting times to be 0, but I'll tell you why it makes no difference. And this gamma ij is an allocation of the item j to contract I. And so the sum should be less than or equal to 1, and this is greater than 0. And these functions are defined 0 outside an interval 0 to Ti. So this is a continuous time problem formulation. But what we showed in a paper which was published in Symmetrics this time, it doesn't matter this continuous time formulation. We can reduce it to a single period problem by just looking at the number of contracts, which is this number n, which is active between 2 points in time. And we need to solve that problem.
So this is the problem faced by each DSP.
Each DSP.
Right, so just clarification. So, I mean, for each targeting group, the DSP can submit a separate bid, right?
No, but we'll see what happens.
Because here you're assuming you know this distribution W winning. So
Right now, that's what we assume.
then you are inferred.
Okay. Right now, we just assume that we know this. So first we need to understand the structure of problem, and then we can do more things. Okay. So you want to minimize. So you can also bring in a more general formulation which includes the parameter Vij, where Vij could think of as what are called the click-through rates. So Coke again has done market study which says that when I show these ads to 100,000 people, maybe 200 people will respond. Okay, so this Vij is known. In this talk, I'm just going to take Vij to be 1, but you can put in this Vij.
In this formulation, the budget constraint implicit or explicit?
Which one?
This formulation, we try to minimize this overall payment. Is the budget constraint involved anywhere?
There's no budget constraint. But I'll talk a little bit about later on budget constraint, but it's not a problem. That is what the previous papers always assumed. They formulated a problem like this, not like this. They just said that I want to bid and I have a budget constraint. And how do I bid? In fact, in none of the previous work was this notion of the supply curve ever brought in.
So in this formulation, you are assuming that there is a way to satisfy the constraints. So
Yeah, I mean, we have to assume, see, because we know if we bid always high enough, we'll always get something. So the constraints will always be, it is always possible to satisfy the constraints.
so there is enough
Supply, there's enough supply so that we can meet these constraints. Now, it turns out, and this is what was the thing, to understand the optimization problem, it's in, you see, for example, let's take this, suppose I take it just over one grid, right? Just look at this problem. So we know these functions fj or the wj are increasing functions, non-negative increasing functions, and there's a whole theory available for optimization of that. But that is simply doesn't help to solve the problem. Okay? And so the first thing is, let's look at what's called the acquisition cost function, which is fj w inverse s by lambda. Is the average cost of acquiring a supply at rate s, given this lambda is just that arrival rate, so you can put lambda equal to 1, but it's just this cost acquisition function. Now, if you take the second price auction and compute all of these things, you realize that this acquisition function is always convex, because w is an increasing function. Okay. So that's the first thing. And in the first price auction, we need a little bit thing, but basically to cut it short, if things are log concave, so if W is log concave, then the first price auction also has an acquisition cost, which is convex. Okay, and then also if it's not a thing, but the other thing we work with is the Spencer transform, which is the convex conjugate, and itself is proper, non-decreasing, convex, and so on, and if it's satisfied, you can show various properties. So this is the problem you want to solve. So I can write that whole cost function in the first part in terms of the acquisition cost function. I've taken the idea, so this is the allocation that if I win J, how much I allocate to contract I to meet the contract I constraints. And obviously the total allocation must be what you got Sj at time. And then what you know is that the solution to this original problem is obtained by just setting the bid equal to the inverse of this distribution function, and you can do the allocation through this Rij and this. So you can solve this whole problem doing this. So of course you can rewrite the whole problem, and you can rewrite this problem in this terms also by substituting. By noting the fact that Rij is equal to Sj, you can substitute this and write this. So this is a convex problem. Of course, here what one must realize is that this matrix Rij is not a full rank. Okay? And so what this thing is it forces R to be constrained in a space of D minus n dimensions, and therefore we need to be able to search for some vector in this dimension as opposed to RD. Where, okay. Sorry. Okay.
So right now you gave us an optimization problem, you're characterizing the
Solution. And so, this comes to the question about adequate supply and whether there exists a solution. We just assume that there's enough supply, but this always happens because you can bid high enough and always acquire items in the market. And the time scale at which these things happen is the following. The time scale at things happen is the time scale of the order of events. So when you open up a web page, there are typically 60,000 such events going on per unit. So the time scale is not a problem in terms of the later results that I've talked.
So just a question. So why do we care about whether R being non-full rank? Because we can always make it inequality, right?
Yeah, but the reason is the following. You know, we can make it inequality, but from an algorithmic viewpoint, it turns out that choose what is called the minimum norm solutions. So the L1 solutions, which are the best, because you can get this sort of nice convex. You can use nice convex optimization to solve this problem. Okay. So the first thing is, of course, if you look at the dual, then the dual gives some. So you can there's no duality gap and so on. And this is a very important thing. You know, there was a previous work, and the previous work on this type of auction was done by Balsiero, and this person at Stanford. This is name. So they had written a paper and they said, look, you know, we got this formulation of this problem. We got this problem. It's non-convex, but yet there's duality gap is 0. And the reason, my belief is, they did not see the convexity in the problem because they didn't have this formulation. So if you look at a dual, then there are these various Lagrange multipliers which say where this Lagrange multiplier belongs to the subdifferential, and what happens is that so this is just one part. So there are two Lagrange multipliers associated with the with those constraints, right? Yeah, you know, there are Lagrange multipliers coming from here, and also you can look at it from a slightly different viewpoint. So there are these two Lagrange multipliers that occur. Let me go back. And there is one Lagrange multiplier which is related to the space of contracts, and one Lagrange multiplier associated with this set of targeting groups, okay, which gives you the price. And if you plug in, what you see is that if you define a function this way, the optimal bid in the second price is exactly the Lagrange multiplier of the problem. Whereas in the first price case, we have to define this function, and the optimal bid in the first price option case is this G inverse times the Lagrange multiplier of the first price case. Okay, so main consequences. The first thing is that the dual variable induce subsets AI star, which are strictly contained in AI, which is the subset of targeting groups that can satisfy a given contract, and BJ star, which is the number of items to bid on. Okay. And secondly, the optimal bids are obtained by mapping the dual solution to a known bid mapping function, and these can be characterized entirely by dual variables or indirectly through what are called the pseudo bids, which are of dimension n. See, one is, remember, n is the space of contracts and m is the number of targeting groups. So this is in the space of contracts. An upshot is the following, is, anyway, so the first thing is, if you look at a continuous time problem, the optimal bid path is constant between contract deadlines. So that means you look at just an interval on which what the number of contracts that are active that have to be bid on that, and it's sort of constant between them. And so it consists, basically your solution consists of your bid path and your allocation path, that at every time you must know what you want to bid, and once you bid and if you win, to what contract you want to allocate. Okay, so now so far we have assumed that we know these functions wj, because once we know these functions wj, we can compute the acquisition cost function lambda j, but in reality we don't know them. So now question is, how can you bid without knowing wj? The problem is, of course, you can do what would you think is a natural thing. Suppose I've got 2 weeks to bid on a contract. The first 3 days I try to take measurements by bidding high enough and learning this curve WJ. And I can do it empirically, I can get it, but that's not good enough because we have to run optimization. Because you need to, and you have no closed form functional thing of this curve WJ. It's not obeying some functional form. So from an optimization viewpoint, it's strictly not very efficient. But it turns out, and I will show you because the thing we have been able to work out is only in the second price auction case, is that in fact stochastic approximation theory comes to our help because of this particular structure associated with the second price
So you're
auction.
not assuming there's no strategic thinking, there's no game theory.
There's no game theory.
Just people are.
But you know what is very interesting is there has been work by this guy Subramaniam, who was a student of Johari at Stanford, where they looked at bidding in, again, they took architectural model and assumed a large number of people are bidding. And what they showed is that at a mean field type of equilibrium, and Balsier also made an assumption on this, is we can assume that from instant to instant when bids take place, because of the mean field effect, the bids are drawn from this distribution WJ, but they are independent. Okay. So the mean field equilibrium gives rise to independence.
So that's okay, but WJ are not satisfying any equilibrium condition.
No.
They're not result of it.
No, you can. No, WJ is only satisfying the condition that it is the distribution of the second highest bid in the system.
Let me ask you differently. Your presence while measuring is going to alter WJ now.
In the case that I said, when I just, if everybody is trying to measure WJ at the same time as I, then everybody is bidding high.
Correct.
So that will affect WJ. But it is assuming that if I am just one DSP and I'm trying to measure WJ, because I got a different contractual deadline, then hopefully I, as a single user, is not affecting WJ.
Right. So atomic effect is.
Yeah.
So this is like a private value thing where everyone has a value for an object,
Right.
which doesn't change with how other people are paying.
Okay. So this is the key solution that helps by looking at this. This is a classic stochastic approximation algorithm. And what you can show is that this entire system, that if I look at a stochastic algorithm approximation, let me just see if I can. Yeah. Look at this. X is the bid, and we know X is W inverse of S. Okay, so here's the S. This is the interarrival client you can think of, no problem. And this is the function that measures whether your bid is larger than the price that other people are bidding for, coming from this distribution WJ. And if you look at this algorithm and these coefficients, let's say A and are chosen as 1 by n raised to alpha such that this condition is satisfied, then what the theory tells you is that really that this dynamics converges, and it converges to the right solution where these quantities, okay, this is very easy, this is a standard thing, but this xn converges to the required bid which you want, which is W inverse X, and this quantity ln converges to bid acquisition cost. Okay. And so you notice one thing about the algorithm. You see, this takes into account the censored observation. Right? Because this says this is 1 only if your bid exceeds the price that is coming out, that is going to be issued at that time. Okay? And so you can basically bid and learn at the same time because you're getting these estimates of the bids, and what you can show is that these algorithms converge to the required bid that you want, and think for a given acquisition rate S.
This is something not clear because the information you're getting is only when you may. So
So you see, this is the thing that tells you getting information only very well.
Agreed, but if there is some underlying W, you're not able to access anything more than this information.
Yes.
Are you
All
saying-
you're assuming is that the prices that are going to
So-
coming from that description.
Right. So given this information, essentially you're saying that I can extract the density function of W, is that correct?
Essentially.
But
Because you need only W inverse of X.
Right, but for any X, so essentially you're giving me the whole.
But you see, I'm only trying to do it for a particular, I'm trying to find a bid at a particular time.
Time is fine, but because W is stationary.
Yeah.
So essentially it gives me.
Yeah, essentially it's telling you you can get that information without taking any derivatives. And you can
But
optimize
if
it.
there is a finite deadline, I mean, there should be some results, some convergence of these algorithms.
Yes, the convergence of these algorithms is of the order of 1 by square root n. The number of events that you get to observe, because it's 100
I see.
milliseconds, you get enough time to converge, even if in the beginning you're not getting the right bit. And I'll show you something. Now the question is that the same thing can be done also in the space of contracts. You know, if I said the two solutions, one is coming in the space of the targeting group, which is what I presented, also in the space of contracts. And in the space of contracts, it's very interesting. It's not a stochastic approximation algorithm, but a stochastic inclusion. That means you are saying xn plus 1 belongs to some f of xn, the set defined by f of xn and the noise. Okay, so it belongs to that. And what you can show is that this set decreases to a point where you get the right thing, when you get the right descriptor. Yeah, if anybody is interested, I can send you the papers. And there's one more thing that I didn't mention, is that we solve for x from these stochastic approximations, but we also have to solve for the r's, which is to which contract I allocated. And to solve that constraint optimization problem, you can actually run a 2-time scale. The first time scale estimates x, the second time scale does the allocation. And again, this is a non-standard stochastic approximation because this stochastic approximation is concerned with a constraint problem. You want to meet that constraint. And since you want to meet that constraint problem, here what happens is that you actually solve it in that smaller dimensional space in between these things. And it's very easy to find that, okay, mathematically. Okay, and what happens is, you know, here is some example. They look at spend item first, second, I think, and here are mean fulfillment. This has to do with the fact that things are random, and on a given interval, if you do these Monte Carlo simulations, this is what you get: percentage of fulfillment on average. And so, in reality, what you would do if you try to solve these problems is put a constraint, so sort of artificially inflate the constraint that you want so that you move slightly higher in the solution space to meet your constraints. And so here's an example of how these algorithms work. And this is the value of A.
So
And
were there any surprising insights you could tell your DSP people who gave this problem to you?
well, we actually gave them the algorithm and we used it on past data that they have. We now got them to buy the data from the exchange on all the prices at every time, because even when they didn't bid, they found that they could have increased their profit by 50% over that period of 2 years. Okay, because they were doing, you know what they were doing is the following. They bid. They didn't win, they increased their bid. Okay? And then they played these games. So initially they tried to, in effect, learn this curve W by bidding high enough to get sufficient number. And then they say, okay, I've got another week to go. I got to get another 20,000 items. And now let me start bidding less. So even if I don't win, it's okay. And then suddenly they realize 2 days before that they still have to get 1,000 on the items. And then they would bid very high to guarantee themselves winning. So that's this type of policy they follow.
Now this is managed much better.
Yeah, and this is managed but better, and the convergence, you see this in 500 iterations, but 500 iterations in the time scale of events that are taking place is very small, because they're taking place at the events of 1 by 60,000 in the time scale of interest. So in some sense, even though initially your bids are not converging, the bids converge rather fast, right? It's this acquisition cost and so on. And the bids converge pretty fast, but yet, you still think that roughly, 200 iterations are needed for this convergence of the stochastic approximation algorithm, but it goes pretty fast. And the convergence rate, we know, in all these stochastic approximation algorithms, can never be better than 1 by square root n, where n is the number of events, because it's a law of large numbers result. You cannot beat it. And this is also some of the curves so this is the supply adaptation algorithm. This is related to the fact that you want to solve the allocation problem. This is the second time scale where you're trying to allocate things. And overall, we found that this is the right theory to do. This is the right answer to this problem. And can anyone find better algorithms to both build and learn? And my belief is no, because you cannot beat anything with respect to the laws of large numbers. Okay, because people ask, one of the things Balseiro asked me, why don't you use, since in some sense what you're trying to do in optimization is take the derivative of that cost function, why don't you use Kiefer-Wolfowitz? But Kiefer-Wolfowitz will not improve the rate of convergence, because the rate of convergence is related to law of large numbers, and that is the governing thing in this convergence, and not whether in some sense you are having a better approximation of the derivative or not.
So if one DSP thinks all the other DSPs are following this optimization problem, can they do better?
I doubt, the game setting now.
Yes,
That's because
Yeah.
it's a real thing, right? You want to look better than everyone.
I believe probably, you can look at the formulation of this problem, but, one of the things that I think that has been studied are looking at game settings of this problem.
Yeah. You want other people to spend more money to get those things, and then when they're out of the game, then you want to buy it.
Cheap. And yeah, I have not looked at that aspect of the problem. So in fact, already one of the aspects of this problem that gets me, really, I think about is when we look at the solution in the space of contracts. The contracts are 1 to n. So when I'm big, one of the things I didn't tell you, one of the things that emerges from the theory, and that's beautiful, it comes because of convexity. It says that if I am a DSP, and so all DSPs, essentially you will bid for all the contracts. If you're trying to acquire an item J that can be satisfied by any of those contracts, the bid that every contract with respect to this item J will be the same. They will not be different. Which makes sense, right? Because I just want to acquire it as a DSP and then allocate it. That's based upon my other constraints. But the mathematics tells you this. That's the first thing. And if you now look at it in the space of contracts now, and now I am a contract and I am looking at the various item types that I have to bid on. I will bid exactly the same on all the item types. So in the space of contracts, I bid the same. In the space of the targeting groups, all the you will bid the same. All contracts will bid the same thing for the same target. And that beauty of that solution that comes about from this convex analysis tells you something very, it has a lot to do with these implementations of these algorithms. And the algorithm, although I wrote it in this very abstract thing as a simple stochastic approximation, proving its convergence is not easy. Okay, and the main reason is because there is a constraint optimization that's going on, and the theory, which I think is the Bible of the theory, is Vivek's book, just doesn't cover it. So we just have to, work hard and do it. So, so that's what. See what we found, and this is the point I was making. The real-time bits for first and second are extremely close, so it is better to use a second price-based algorithm to compute the bits. Because this also requires less regularity, because we don't see the problem in the first price auction case is actually coming, and that's why it's much harder to show things in the first price auction. It comes to that evaluation function G, right, where you need the derivative W. In the second price auction case, this G is identity. And so, this causes the problem in the first price case. This whole thing. But when you actually run the numerics on the first and second price auction, for any curve W that you can produce, right, the bids are very, very close, almost identical. And that makes sense because you have to win. And it's only after winning, the first price or second price tells you is what you have to pay. So the payment in the case of second price auctions is low, but the bid tells you should be approximately the same. They're not identical, but they're approximately the same.
So just as a thought experiment, so consider the universe that there are only two DSPs.
Yes.
And both of them are running the same algorithm. So what will happen?
Then this theory goes through. As long as they're playing along this.
No, so let's say there are no other DSPs.
Yeah.
There
No,
are
but then what would happen
yes.
is this role of WJ would be very different.
Yes.
Because they would be very coupled.
Right. So in that case, I think you have to break the symmetry in some way.
Yeah.
You have to inject some randomness into the algorithm.
Or you will have to do more of a game theoretic solution. Because what this theory really assumes is this curve WJ is really coming from the mean tree of a large number of players who are trying to bid. Right? And it's only when you take, if you take two players, it's a minimum of two random variables. And suddenly, when the number of random variables is very large, you get very nice structures associated with the distribution of that maximum. Right? In fact, what we know is from the work of all of this Sigmund and all that, when you have a large number of them, there's a very nice asymptotic thing, right? Which when n is large on the max of these random variables, which has a nice distribution. And that seems to be playing a role. And I believe that was the type of analysis used in that paper by Subramaniam and Johari. So with that, I will stop. And if anybody is interested in the paper, I believe out of all these papers, this is the nicest paper, and I can send it to you because this explains the whole theory. Because now we understand it. Okay. And so, like I said, this was a paper which really got me, first ideas of the problem. But in this paper, they only consider one targeting group. They considered IID observations, and so there was no such problem. The allocation problem did not exist, or the bidding algorithm. And what they showed, there is a very famous paper. I don't know whether it's here. Yeah, this paper of Gumadi, Key, and Proutier. So I didn't talk in this talk about budget constraints, but you can put budget constraints in the problem, and the only thing that really changes when you put budget constraints is that the bid is no more x, but what is called a shaded version of x, which is x upon 1 plus some thing and actually turn it into a Lagrange multiplier. And that Lagrange multiplier comes from the budget constraint. So that means you don't bid exactly, but you shade your bid and you sort of lower your bid. So in terms of the theory that I said, you have to actually increase your bid to get the WTX. Okay. So Gumardi and Putier showed that you have to shade your bid, okay, by looking at the budget constraint problem, saying that if you're bidding X, because they took a discounted cost problem, okay, rather than a vertical average problem, the discounted problem along with the budget constraint gave the shading factor. Okay. And what Santiago said, okay, I'll assume the shading is present, but the shading factor depends on the distribution from which you're trying to calculate it. So how do I calculate the shading factor? And so essentially this paper was on how you calculate the shading factor given that you don't know W. And so they talked about the whole theory there. And so our work was really looking at this problem from various. So the first paper, you see, we just assumed there were increasing functions, and we didn't assume any differentiability. And not having this idea of the convexity, we didn't really have algorithms, efficient algorithms in that first paper. So in this paper, we realized that you can formulate the continuous time problem, but it really, it all reduces to just looking at it in one period. Right? Just look at the number of guys who are active in that period and just solve it in that. So it just becomes a one period problem. And we noticed, by this paper, we really noticed all the convexity designs, the convexity of the problem. But finally, in this last recent paper, which is sort of the culmination of the PhD thesis of the student, we completely understood the implications of this convexity theory and the primal dual properties associated with the solution, which then, in fact, is what we're doing now for looking at it from the learning viewpoint. The stochastic approximation theory is very, it's not that, what is the right word? It's standard, but non-standard because you have to show things, right? But the theory is not surprising. So that does. Thank you. Sorry, I took up the whole hour.